Hello, and welcome to our listeners around the world. You're listening to JAMAevidence, our podcast series based on core issues in evidence-based medicine. Today, we're discussing nonparametric statistical analysis. I'm your host, Dr. Roger Lewis, Senior Statistical Editor for JAMA and editor of the JAMA Guide to Statistics and Methods series. I'm here with John Lachin. Dr. Lachin, can you go ahead and introduce yourself for our audience?
Thank you. I'm an emeritus research professor of bioinformatics and statistics at the Milken Institute School of Public Health at the George Washington University, where I have been a member of the faculty for the past 50 years.
Great. Thank you very much, John, for joining us. So in discussing your article about nonparametric statistical analysis, let's start with the opposite. What is a parametric statistical analysis?
So many analyses start with a statistical assumption with respect to the distributions of the variables that are employed in the analysis. And these distributions can be characterized by a small number of parameters. For example, for the commonly used t-test, the parameters are the mean values within each of the two groups to be compared, and the standard deviation among the values in each group. And so such an analysis starts with an estimation of these parameters, and on that basis, it's considered a parametric analysis.
So for the t-test, the parameters of the mean and the standard deviation completely describe the normal distributions that are assumed for the data. So what do we assume about the distributions in a non-parametric analysis?
All right, so the most common non-parametric analysis is a rank-based analysis in which the ranks of the values are substituted for the actual values, and these are then used to assess whether or not the shapes of the distributions, regardless of what they might be, differ among the groups.
I think it's useful to be a little bit more explicit about what is the ranking process. So, John, if you had two groups of measurements, say on two different groups of patients, how would you actually go about ranking them?
So you would combine the two groups and then order the values from the lowest to the highest. And it doesn't really matter whether you order them in an ascending manner or a descending manner. You will obtain basically the same p-value for your statistical test if that's the analysis that you're conducting.
And so you actually use the ranks as the values instead of the measurements you actually made?
Precisely, yes.
Okay.
And, in that case, under the null hypothesis of no difference between the groups, each of the groups should have a similar fraction of high ranks and intermediate ranks and low ranks within the two groups.
So what are the advantages of taking this approach?
The principal advantage is that you can obtain or conduct a very powerful analysis without the need to specify any distributional assumptions, so that this approach will provide a robust or a sensitive test of the difference between groups, regardless of the shape of the distribution.
Now, let's suppose hypothetically we didn't know about this approach and we used a traditional t-test which assumes a normal distribution on data for which the values weren't normally distributed. What kind of trouble might we get into?
Well, there are a number of potential adverse effects, shall we say, of misspecifying the assumed distribution in a parametric analysis, whereas in a non-parametric analysis, the analysis is valid and will provide a test with the desired type 1 error probability, such as 0.05, regardless of what the actual shape of the distributions are in the two groups.
So in a sense, the non-parametric approach allows us to get the characteristics of the test in terms of its risk of a false positive or its risk of a false negative that we think it should have. Is that fair?
Yes, right.
So, one of the areas of statistical analysis that is most common in the pages of our journal is the use of regression techniques, whether they're linear regression, logistic regression, or regression, say, for survival analysis or time to event endpoints. Many of those regression techniques do make parametric assumptions about the things we're trying to understand. Are there non-parametric versions of those regressions? And if so, what should readers know about them?
Indeed, there is an approach that would allow the conduct of regression models or regression analyses using the ranks of the observations. And this is called a rank transformation analysis. And it's been shown that the rank transformation analysis provides the same robust benefits of providing a valid test with respect to its control of type 1 error, regardless of the actual distribution of the observations in the study.
So, in your article, you mentioned the use of a non parametric approach to ANCOVA or analysis of covariance, specifically in the setting in which you wanted to adjust for baseline measurements in an analysis. Can you talk to us about how that works?
Okay, so the analysis, called a rank transformation analysis, would employ the ranks of the baseline measurements of the subjects in all groups combined, and then separately the ranks at the follow-up visit among all subjects combined. The analysis has been shown in this case to provide a similar improvement in power as would be obtained in a parametric ANCOVA, and also preserves the type 1 error probability of a false conclusion.
So, essentially, this approach allows you to get the advantage of adjusting for the baseline values with the improvement in the signal to noise while preserving the correctness, if you will, or the validity of the statistical tests for each of those associations. Is that fair?
That's right.
Okay. John, since we've talked about some of the advantages of the non parametric approach, it's only fair that we also talk about the disadvantages. So, what are those?
One of the principal disadvantages is that the rank-based analysis is using the ranks themselves rather than the actual observed values. And because of that, the rank-based analysis does not provide estimates of the parameters that would be employed in a parametric analysis. So as a result, the non-parametric analysis does not provide confidence limits on the parameters of the distribution of the observations. In that case, there could be a discrepancy between the result of the non-parametric test and the estimates of the parameters. So it's possible that the Wilcoxon test would be significant, whereas the difference in the means would not provide confidence limits that reflected the results of the Wilcoxon test of significance.
John, in your article, you used a specific example of a clinical trial comparing doxycycline versus placebo and its effect on aneurysm growth among participants with small infrarenal abdominal aortic aneurysms. Tell us a little bit about that study and why they needed to use a non-parametric approach.
So there were two groups of subjects, and the nature of the outcome that was employed required that, in essence, the authors use a non-parametric approach. So this was a study comparing subjects assigned to doxycycline versus placebo with respect to aneurysm growth over a 2-year period of follow-up. During the study, a number of subjects died or had surgical repair of the aneurysm. And for these subjects, there is no outcome measurement that was obtained at 2 years of follow-up. However, information about these subjects is informative in the sense that we know that these subjects had a worse condition at 2 years compared to other subjects who were still alive and still free of surgical repair at 2 years. So to implement that analysis, worst ranks were assigned to the subjects who died, and then the next level of ranks was assigned to subjects that had surgical repair, and the remaining possible ranks were assigned to the subjects who survived and were free of surgical repair. So this could not have been done in a parametric analysis.
So, John, in thinking about non-parametric analyses, what do you think the key takeaways are for our audience?
So the principal advantage of a rank-based analysis is that the resulting statistical test result, the p-value, is valid regardless of the underlying shape of the distribution of the values within the groups being compared.
I am Roger Lewis, and I've been speaking with John Lachin about non-parametric statistical analysis. You can find a link to the article in this episode's description. This episode was produced by Daniel Nassisi at the JAMA Network. To follow this and other JAMA Network podcasts, please visit us online at jamanetworkaudio.com or search for JAMA Network wherever you get your podcasts. Thanks for listening.
This content is protected by copyright by the American Medical Association with all rights reserved, including those for text and data mining, AI training, and similar technologies.